Hello! In this video I will explain the steps of basic procedure of Gauss elimination to solve a system of linear equations and how to implement it by using a Python code. As you see here, a linear system is a set of equations. The number of equations should be equal to the number of unknown variables, x. The a's are the constant coefficients of the variables, and the b's on the right side of the equal signs are the constant terms of the equations. The system can be expressed by using the matrix form, which will give us a matrix vector equation of three components. On the left side, the coefficients matrix multiplied by the vector of unknowns, or vector of unknown variables, and on the right side, the vector of the constant terms. To make the explanation of the elimination procedure simpler, a superscript, shown here in the parentheses, is added to every constant to indicate to the elimination step. As you see here, the original system has 0 eliminations for all elements. The goal of this stage is to transform the system so all elements under the main diagonal of the coefficients matrix become zeros. In the first elimination, the first row will be fixed. We may call it the reference row for the current elimination. So, the elements of the first column below the main diagonal will be transformed to 0. Each row in the system under the fixed row should be multiplied by a factor. The factor is equal to the main diagonal element corresponding to the fixed row divided by the first element of the corresponding row. So, the factors will be A11 divided by A21, A11 divided by A31, and A11 divided by A41. This will make all elements under A11 equal to A11, while the other elements in each row, including those in the B vector, will have different values. The next step is to subtract each row multiplied by its factor from the fixed row to have 0 elements in the first column. At the end of the first elimination, only the first row remains without any changes, while all rows below it are subjected to the first transformation as their superscripts show. We can write the calculations separately. So as you see here, the element A21, the first transformation, will equal to A11 minus A21 multiplied by the factor of the second row, and so on. And also, we see that the calculation of the B2, the first transformation, will be equal to B1 minus B2 multiplied by the corresponding factor. In the second elimination, we repeat the same steps. The second row now is fixed in order to zero the elements A32 and A42. So we multiply the rows 3 and 4 by the factors A22 divided by A32 and A22 divided by A42 respectively. Then we subtract the 2 rows from the fixed row. Thus we get the elements of the second column under the main diagonal transformed to 0, and the other elements have new values of the second transformation. These calculations can be represented by these equations. As you see here, there's still only one element has to be changed to 0, which is A43. So exactly as we have done before, we multiply the last row by A33 divided by A43. Then we subtract the row from the fixed row to get the final elimination. Accordingly, we can write the final calculations as following. At the end, we get the whole system eliminated as aimed at the beginning. It is important to notice here in the final system that only the first row in the coefficients matrix and the corresponding constant term remain without changes, while all rows below it have been transformed. As the colored superscripts indicate, the final second row is resulted from the first elimination, and the final third row is resulted from 2 eliminations, and so on. We start the stage of back substitution from the transformed system. In this stage, we don't need the superscripts of the elimination steps, so we can neglect them with keeping in mind that this is the final system after the elimination. To explain the remaining steps, let's perform a matrix multiplication to the system. So we obtain the following equations in this order. So the first equation, the second equation resulting from the second row, the third equation, and the final equation. It is clear now that the values of x can be calculated starting from the last equation, then by substituting the known x values into the prior equations up to the first one. That's why it's called back substitution or backward substitution. So we can write x calculations as following. So starting by x4, then x3, x2, and x1. As you might notice here, in these calculations, there is a specific pattern of subscripts. Each value of x is found by the corresponding b value minus previously known x values multiplied by their coefficients, and all are divided by the corresponding main diagonal element. The coefficient matrix elimination formula can be written as aij asterisk, or let's say star, equals to akj minus aij multiplied by the factor akk divided by aik, where a star is the new value of aij in the current elimination. The subscripts are k, where k is the index of the fixed rows, so it goes from 1 to n minus 1, the one before the last row. I is the index of the rows under the fixed one, so it should start at k plus 1 and goes to the last row n. To perform the multiplication and subtraction of each element in any row, j is the index of the columns, and it should include the column corresponding to the fixed row, as we saw before, so it should be from k to the last column n. Finally, the element of the vector of constant terms are subjected to the same operations, but because it's one column vector, it doesn't need j index. If any of the elements under the main diagonal is already 0, the whole process of elimination for that row should be skipped or jumped over. For example, in the first elimination of this matrix, the third row should not be transformed because it already has a 0 element in the first column. The back substitution starts by calculating the value of xn. Then the remaining x values starting from equation n minus 1 to the first. Of course, the summation should start from j equals I plus 1 since xi is the unknown, while all x values up to xn are known from the previous substitutions. Up to this point in this tutorial, we used the common index or subscript system for matrix and vector elements in the textbooks and references of linear algebra and mathematics in general, where the index of the first element is 1 and the last element is n, as shown here. But when it comes to coding you should take into consideration the array index system of the computer language you use. For example, the array indexes in Fortran and MATLAB start from 1 by default. But in Python and C++, for example, the first element of an array has index 0, and for n number of elements, the last element has the index n-1. Let's make a small test on Python shell using lists and NumPy arrays. Now, as you see here, we can start with lists. So let's create a simple list of A, and let's say it is 3, 6, 9, 12 elements. So these are the elements of this array. Now, imagine if we want the element number 1, so let's say A1, so it will be 6. Why? Because A, the first element actually, has the index 0. So if I use A0, I will get 3. In Python lists, we have a function called index. For example, if I want to know the index of 12, I can say a.index 12. So in this way, we know that the index of the element 12 in the array A is 3, not 4. Because if I call A4, I will get an error message saying that list index out of range. That means I gave an index number which is larger than the largest index or the maximum index in the given array. The same thing can be applied for NumPy arrays. For example, let's import first the NumPy as MP. Then let's create b mp.array. Let's say 4, 7, 2, 9, and let's say they are float. Now, again, the same way. If I say b 3, I will get 9. For this reason, the subscripts of the system should be like this. From now to the end of this tutorial, I will use the Python index system, so please pay close attention to this point. The algorithm of elimination part requires 3 nested loops. The first is the k loop, which specifies the fixed rows. According to Python index system, it should start at 0 and end at n-2. The second inner loop is the I loop, which applies the elimination to the rows below the fixed row. In this loop, we check for 0 element before elimination, calculate the factor of each row, and calculate the b vector element transformation. The innermost loop is the j loop, which performs the calculations of the element of each row on the corresponding column. Please notice that the calculation of the b vector element can be put just after computing the factor, since it does not depend on the innermost loop. I put it here just to keep it in the same sequence shown in the theoretical explanation in the previous slides. The algorithm of the back substitution starts with the calculation of x in the last row first. Then we use 2 nested loops. The first goes through the equation from n-2 to the first equation. Since the loop will go backward, during the coding, its step should be set to -1. The inner loop is to calculate the summation of the x's multiplied by the corresponding a's of each equation. Finally, in the outer loop, the value of the current x is found. In this algorithm of back substitution, we have to put the calculation of xi after the j loop because it depends on the sum ax value. Before coding the method, let's solve this example by applying the procedure and find the solution in order to check it with our code later. First, we put the equation in the matrix form. Then we use the Python index system in order to express the elements in the matrix and the vectors. To simplify the hand calculations, let's put the system in a simpler form. Our goal now is to zero the elements below the main diagonal. So first we define the fixed row and the first column to be eliminated. So we calculate each factor corresponding to the row that it would be multiplied to. So after multiplication, we will get this system. So as you see here, the elements under the first or in the first column are all equal to 3. So by subtraction from the fixed row, we will get the elements in the first column under the main diagonal eliminated. Now we repeat the same procedure by fixing the second row and defining the two elements in the row number 2 and row number 3 under the first column to be eliminated. Now we calculate the corresponding factors. Then after multiplication, we'll get this system. As you see here again, the elements under the main diagonal of the first column are equal to those or to that in the main diagonal corresponding to the fixed row. Now, after subtraction, we will eliminate these two elements and get this system. Finally, we fix the row number 2, and we have only one element to be eliminated. So we multiply in one factor, we will get this system. So as you see here, we can eliminate the remaining element by subtraction to get the final system, which has zeros under the main diagonal. Now we go to the step of back substitution, and simply just by multiplying the rows and the corresponding values, and we get the following results. So x3 will be equal to b3 divided by a33. So we start from the last row, then we calculate x2 in the same way. So since x3 now is known, we can substitute it in the equation of x2 in order to get the value. Then the same way, since we know x3 and we know x2 from the previous substitutions, we can calculate now the value of x1, and finally in the same way we get x0. So now we can set the values in the correct order to get this result. Let's start coding by first importing the required functions. So we start by from NumPy we need two important functions, which are array to create NumPy arrays and zeros to initialize an array. Now we define the A, which is coefficient matrix, as an NumPy array as following. We define the type as float. We define the constant terms array. Now we can use the function len or length to define the size of the system. And we initialize or define the x or the solution vector. Now let's start typing the elimination stage. You maybe notice here that I used n or range n minus 1. This statement will start from 0 as default, because range always it assumes that we are started from 0. But when we say n minus 1, actually we know that the Python loop, by using range, will go to n minus 2, will go to the element just before the mentioned here. So this should be kept in mind while we make the loops containing the last element or the last point. Again, the same point here. So we're supposed to go to n. For loop I, we should supposed to go to n minus 1, but because we know that the for loop in Python will go always to the element just before the last mentioned in the range statement. Now let's print the transformed A matrix and the transformed B vector and compare the results with the manual solution. Save the code, and so now we can start coding the back substitution part of the solution. This statement, before proceeding to the next statements, let me explain why I used these parameters in the range statement or range function. So n minus 2 refers to the equation or the row just before the last one, because the last one is n minus 1, so the index of the one before will be n minus 2. Now, here we are going to use minus 1 instead of 0, because at the beginning you may think that we need to put 0 here because we want to go from the n minus 2 row to the first row in the matrix or in the system, which is 0. But actually we know well that the range function in the for statement in Python will not stop at 0. Actually, it will stop at 1 if we use 0 here as it is now. So in order to make the loop or the value of I stop at 0, we should take one element after it. So it will be minus 1. Of course, since the loop is descending, it's not ascending, it's descending. It's going down from a big value, which is n minus 2, to smaller value, which is supposed to be 0. So that's why the step size or the step of the loop should be negative. Now let's continue typing of this part. So it will be equal 0. So finally, we should print the solution. Now let's run the code and see the results. So as you see here, we have obtained the exactly the same solution as the manual solution, and that shows that the program is working correctly. In the next tutorial of Gauss elimination method, I will show you how to make important modifications in order to solve systems with special conditions. If you like this tutorial, please give a like and do not forget to subscribe and turn the bell to be notified for the coming tutorials. Thank you.